This is Chapter 4, Crossing the Charges of Ions to Make Neutral Compounds, Introductory Chemistry at Mineral Area College. So here on the right side of the screen, I just have a table that we can use to reference throughout all these examples. So I have group 1, 2, 13, 14, 15, 16, 17, 18 from the periodic table because those are going to be the common ions that we're going to be dealing with, the ions from those group numbers. So the first one we have lithium bromide. Lithium is going to be from group 1, so it has a positive charge. Bromide tells us that bromine will turn into an anion whenever it makes ionic bonds because the IDE suffix tells us that it's going to be an anion. And so group 17 is going to have a -1 charge, so it's going to be Br-1. And so in order to make ionic compounds, we can just kind of think about it logically. So if I have one lithium that's going to give up an electron, and I have one bromide that's going to gain that same electron, I can just write my formula as LiBr because I just need one of each to satisfy each other. However, that is going to be different for different compounds. And so, for example, potassium nitride, potassium is going to be from the first group. It has a +1 charge. Nitride tells us that nitrogen will turn into an anion as it makes an ionic compound because of the IDE suffix. Nitrogen is going to be from group 15, so it has a -3 charge, so it's going to be N-3. And so we can still use the same process from the first example. So if I have one potassium that's going to give up an electron, and I have one nitride that's going to gain those 3 electrons, right? Because it has a -3 charge, so it's going to be 3 more negative. Then I will need 3 potassium ions and 1 nitride ion or nitride, simply because 3 potassium ions are able to give up 3 electrons for 1 nitrogen to gain those 3 electrons. So our formula will just be K3N because there's going to be 3 potassium ions that's going to give up those 3 electrons. That one nitride is able to gain those same 3 electrons. So next, we're going to understand this concept mathematically because later on, whenever you guys just get through more complex compounds through ionic bonds, it's kind of difficult to try to apply this sort of same process. We can for sure apply the same process for calcium oxide, but I would just like to show you guys the mathematical version as well. So calcium is going to be from group 2, so it has a +2 charge. Oxide tells us that oxygen is going to turn into an anion whenever it makes ionic compounds because of the IDE suffix. So it's going to be from group 16 and it has a -2 charge. So the rule is we're going to find the least common multiple, or the LCM, of the charges. In this case, 2 and 2. We're going to be using the absolute value of both the charges, so just only the positive values, because it will help us later on with the multiples and it will just be a lot cleaner, and you'll see why in a second. So then we're going to divide the LCM by each ion's respective charge. The quotient will become the subscript of each ion. And so what I mean by that is, say for instance, you found the least common multiple, or the LCM, of calcium. So calcium has a 2 charge, right? And so to find the multiples, all you got to do is just multiply 1 times 2, 2 times 2, 2 times 3, and so on, so on, and so on. This can go on forever. But I just stopped here just to show you guys that 2, 4, and 6 are multiples of 2. And if we're going to use that same process, we're going to be using +2 for this example, or just like the mathematical expressions in general. And so it's going to be 1 times 2, 2 times 2, 2 times 3, 6. So it's just going to be 2, 4, and 6, which are the multiples of 2. Now, even though these are the multiples of 2, we want the least common multiple of the set of numbers, like the 2, 4, and 6. And 2 is obviously going to be the least common multiple because it is less than 4 and less than 6 as well. So we're going to take that least common multiple, which is 2, and we're going to divide it by 2 as well because the overall charge was 2, correct? And so it's going to be equal to 1. Same with oxide. Oxide had the least common multiple, or the LCM, of 2, but since it has a 2 charge, we're going to divide it by 2 as well. And we're also, whenever we're dividing, we're going to be finding the absolute values of each charge, meaning that it's all going to be positive, it's not going to be negative, or else it's going to mess up our numbers, because obviously we can't, if we did 2 divided by -2, then it would be -1, and we can't have a -1 subscript, right? So the formula is just going to be CaO. And this is simply because there's one Ca and there's one O. And we know that because we just found the subscripts for those. So next we have magnesium nitride. Now magnesium is from group 2, so it has a positive 2 charge. Nitrogen is going to be from group 15, but since it's IDE suffix, it's an anion, so it's going to have a -3 charge. So it's the same process. We're going to find the least common multiple, or the LCM, of the charges of these ions. In this case, it's going to be 2, +2, and +3, and then divide the LCM by each ion's respective charge. The quotient will become the subscript of each ion. So in order to find the least common multiple, or just the multiples of 2, we're going to do 1 times 2 is 2, 2 times 2 is 4, 2 times 3 is 6. To find the multiples of 3, we're going to do 1 times 3 is 3, and 2 times 3 is 6. And I stopped right here because I know that their first common multiple of 2 and 3 is just going to be 6. And if I kept on going further, they might have the same, multiples such as 12 or 24, but those aren't the least common multiples. 6 is the least common multiple for 2 and 3. So next we're going to divide the LCM by the charges. And so 6 is the LCM. We're going to divide that by 2 because magnesium has a positive 2 charge. So it's going to be 3. 6, which is the LCM, divided by 3 equals 2 is going to be the subscript for nitride in this ionic compound. And notice how I didn't, again, divide by -3, because if I were to do that, then I would have -2, which is kind of impossible because you can't have, a negative quantity of something. And so our formula is just going to be Mg3N2. So on our next example, we have aluminum kryptonite. Now, aluminum is going to be from group 13 on the periodic table. It's going to have a +3 charge because it doesn't have the IDE suffix because it's a cation. And then kryptonite. This one is sort of strange one because if you think about it, kryptonite does not exist. And I just put this in as an example just to show you that certain compounds, ionic compounds, will never exist. And kryptonite is one of them. Kryptonite is not even an actual ion. I just made that up for the sake of this video. But basically, krypton is going to be from group 18. Group 18 is going to be where the noble gases lie. And so group 18 has a 0 charge, and so it's already stable. It's not going to want to bond with any other ion in order to become more stable because it's already stable. And so kryptonite is just something that I just made up in order to just make a point that certain ionic compounds cannot exist, such as, noble gases. Noble gases cannot turn into ions, and so they cannot be a part of the ionic compounds. Thank you for watching.